My name is Mayank Shekhar and my project report is about image compression. Here we'll be discussing about three algorithms for image compression. One of those is DCT, second one is wavelet transform, and the third one is winner takes all. So I'll try to outline what I'll be discussing for the entire project, what I have done. Image compression is a very important aspect in today's world, which is why it has become very essential. One of the reasons for this is most of the image they have a very high quality size in them, and not all of the information in those images are needed. Because of which a lot of storage space is gone. So one way to overcome this problem is to use image compression. The compression algorithm allows us to construct an image such that the storage size of the image is reduced, but at the same time important information in the image is not lost. Image compression can be applied in two ways, one of which is lossy and the other one is lossless image compression. Of course, in lossy image compression, the size is reduced considerably. However, in lossless, the size is not reduced by that amount, and yet the texture of the image is retained. Next, I'll be talking about autoencoders. Autoencoders are neural networks, and they worked in an unsupervised manner to reproduce the input given to them. One of the kind of autoencoders is sparse autoencoders, and two other transform coding algorithms are used for image compression. The algorithms compared are based on discrete cosine transform and wavelet transform. These three techniques are compared using different data sets and their performance are evaluated. We'll be talking about neural networks, which have been found to be highly efficient and accurate in tasks of classification, especially when used for image data set. Here we can see autoencoder in action, where the layer 1 is the input layer where we present the images to the network. Layer 2 is known as the latent representation of the input image, and the layer 3 we get the approximate version of the original image. By turning our parameters and reconstruction error, we can obtain a compressed version of our original input image. For our discussion in this project, we have used a sample dataset of Caltech 256, which consists of 256 categories of image and 30,607 images. Next, I'll be talking about what is DCT and wavelet transform. So this is just an introduction about DCT. DCT can be used in digital image processing for the purpose of pattern recognition and Wiener filtering. DCT's performance is compared with the class of orthogonal transform and is found to compare closely to that of Karajan-Loew transform, which is known to be optimal. The performance of Karajan-Loew and discrete cosine transform are also found to be compared closely with respect to rate distortion criteria. It considers the higher frequency in a pixel for the image rendering, thus typically reducing the number of pixels in the image and hence augmenting the compression of the image. Wavelet's formula, which is the representation of a square integrable real or complex value function by a certain orthonormal series generated by a wavelet, which is preferred over Fourier transform because of its practicality in image compression. This is expressed in the following equation. Now I'll be talking about unsupervised learning. Unsupervised learning for an image compression, it is an algorithm that learns the input mapping from variable x1, x2 and xn to an output variable for a function y equal to fx. So what we do here is that this unsupervised learning, it takes some input and based on those input, it learns the behavior of the function so that next time when an input is fed to that algorithm, it tries to project the output. However, the goal of an unsupervised learning is to model the provided distribution or structure in the data in order to learn more from the data. It assists in solving the aforementioned supervised learning problem by using convolutional architectures. For image compression, this goal of predicting mapping becomes one of the problem, which comes from the fact that the size of the receptive field in neural network is small, because of which the relevant features in an image are not captured. One way to overcome this is to increase the hidden nodes for representation of all features. That again increases the size of the data to be stored, hence diverts from the aim of image compression. An underlying consequence of this is whatever features we learned over a small patch sampled randomly over a larger image, we can apply such a small patch in the form of a 2 by 2 matrix or a 3 by 3 matrix learned feature anywhere in the image. Now it does this in 3 steps. The first step is convolutional. In natural image, we have the property that there are stationary objects, which means that the feature of one part of the image is same as any other part. This implies that the feature learned from one image can be applied to any other part of the image, even at all the locations. We can emphasize the fact that we can take this learned small patch feature anywhere in the image and convolve them with the larger image, which provides us with a different feature activation value at each location in the image. The second step is max pooling. Max pooling is a sample-based discretization process. It is used to sample down an input representation hidden layer output matrix image, which reduces its dimensionality and provides assumption about features contained in sub-region bin. This is done in part with overfitting by providing an abstract form of the representation. It also reduces the processing cost by reducing the number of parameters to train, and provides basic translation invariance to the internal representation. It is implemented by applying a max filter to a non-overlapping subregion of the initial image. So an example of this would be if we have a 4 by 4 matrix that represents an initial input and we have a 2 by 2 filter, then we'll run over the sampled image. We'll have a stride of 2 for stepping over the input will be 2 by 2 without any overlapping. Now for each regions represented by our filter, we will take the maximum of the region and create new matrix, which will be our output, where the elements would be maximum of the region in the original image. Now I'll be talking about autoencoder. Autoencoder is also known as auto-associator or diabolo network. It is an artificial neural network used for unsupervised learning of efficient codings. Next, I'll be talking about the winner-take-all auto-sparse encoder. It is an algorithm that falls under the category of unsupervised learning algorithm for training convolutional encoders with a very strong sparsity constraint on the activity bounded by each feature map. It is used for encoding a set of data for dimensionality reduction. Autoencoder applies backpropagation by setting the target value equal to the inputs. In other words, it is trying to learn an approximation to the identity function. Hence, we can reduce the number of hidden units and can discover interesting structure about the data. It provides a technique for directly learning a convolutional autoencoder. This algorithm uses all aforementioned learning literature. As an example, we'll consider the filter that was learned in convolutional fashion used in the proposed architecture of sparse convolutional autoencoder with just 32 filters, while keeping the size of the receptive field the same as the patched model. For this scenario, we can see that one filter is allocated for detecting each of the orientation, which is depicted in the image below. Now we'll be talking about compression using transform coding algorithms. The next class of algorithm are based on transform coding approaches that we briefly described above. The discrete cosine transform and wavelet transform. Discrete cosine transform, we exploit the sparsity of the images to produce version of original image. For our task, we chose the discrete cosine transform as it basically consists of sinusoidal components, and it is well known that any image can be effectively represented by a combination of sines and cosines. In this method, we assume that our image is generated over linear combination of coefficient vector and a set of basis vector which form a dictionary. We pick a dictionary which can produce highly sparse result with low errors. Now we will be talking about wavelet transform. Wavelet transform are widely used in many image processing applications such as image compression and feature extraction. We compress the images by using 2D analysis. We start by choosing mother wavelet, which we have chosen as a Haar wavelet. The image is further decomposed by a level n which has been taken as 3 and 5 in the project. The image compression is based on improving I2 norm of the recovery. Now, coming back to DCT algorithm, I'll be discussing how this algorithm works. Initially, we input an image, then create a 3 separate plane which converts into RGB distinction. Now we create a row vector consisting of different value of coefficient that you want your model to be. Now we create a 2D DCT matrix for each of the k values where the output of 2 DCT is Rn cross k for num rows in DCT and for num columns in DCT. Now we take the coefficient of these row and column and do a dot product. Image component equal to image component plus the coefficient of row and column into DCT, where image component is compressed image obtained. Next, we are going to talk about the related work. In the recent years, there have been a number of development in the field of compressed sensing, which have produced highly efficient algorithms for image compression. Some researchers have used a wavelet lifting scheme. They use 3 different measurement matrices and have used orthogonal matching pursuit and basis pursuit algorithms to compute best coefficient in final model. Recently, neural networks have used for dimensionality reduction in datasets. Many such architectures have been extended for image compression tasks as well. We know that image compression is one of the most useful application of image processing. There have been multiple algorithms that have been designed for this task. They have compared their results on basis of PSNR and SSIM values. They have shown that the wavelet lifting scheme coupled with use of random orthogonal matrix and orthogonal matching pursuit algorithms gave the best results. Autoencoders are used for compression, which are based on recurrent neural networks. Finally, we will be giving a conclusion of this presentation, after which I'll be demonstrating what we have implemented in algorithm. So the experiment done in this project proved that the performance of a neural network is far better than the traditional algorithms, both in terms of quality of the compressed image as well as the time taken to generate them. The only drawback with using a neural network is the amount of training data they need to produce compressed images without loss of important information contained in them. Also, the neural network model do take a lot of time when it comes to training, but are faster during testing. The output generated by DCT took a lot of time when the number of coefficient included in the model increased above 64. The result did enforce the fact that the winner take all encoder are in fact the state of the art in task of image compression. That's all for this presentation. Now I'll be showing you how to run the code in MATLAB. So the first one is using the wavelet transform. This is using a Haar wavelet and decomposition is 5. Now I'll be running the program. So we see the compression has been done from figure 1 to figure 2. Next, we'll be moving to DCT. Here the value of k, which is the number of coefficient, is set to 32 currently. So this is the original image. Now we'll be waiting for the result. So this is the compressed version of the image. As I had mentioned earlier, DCT takes relatively longer time because of the computation and the coefficients. At last, I'll be showing the winner take all algorithm of predicting the output of the compressed image. So this is the final result which we have seen, which we are seeing. It is implemented using Keras deep learning libraries in Python and Thanos as the back end. So this is the final output generated.